G'day and welcome to the first video for topic 2 of week 10. So as I said during topic 1 was big. It covered a lot of material, but it was best to treat it all as one big lump, which was why we had a big topic to start the week with. This topic and topic 3 are both smaller. They're both dealing with parts of heat transfer, heat methods. So we'll spend a bit of time on these, but it shouldn't take anywhere near as long as you spent on topic 1, which is all about problem solving with calorimetry. As usual, we'll jump over and we'll get started on the slideshow and work through this topic. Conduction and convection. So far, we've talked about, as I said, calorimetry and what heat does to materials, but today we're going to cover the 3 mechanisms of heat transfer. We'll actually talk about the third one in topic 3, but we'll introduce it today. We're going to be able to define conduction, calculate the rate of heat flow through a conductor, explain how conduction influences the feeling of temperature, define thermal resistance, and then define convection and explain how it occurs. That says conduction, that should say convection. I will edit that at some point, hopefully, but we're talking about convection and conduction. The process of heating is the way in which a substance gets that heat energy that we've been talking about. We've already talked about what happens once it gets it. When it gets it, it either rises in temperature, sensible heat, or it uses it to change phase, which is latent heat. So we're talking about what the substance does with the heat energy that it gets, but how does it actually get that heat energy from some other object? How does that thermal energy, that internal energy, transfer between 2 different things? There are 3 different ways. We call them the heat mechanisms. They are conduction, convection, and radiation. As I said, the first 2 will be covered in this topic. The third one, radiation, we'll look at tomorrow, just because it's a little bit different from these 2. So the first 2, conduction and convection, involve heat transfer or energy transfer by molecules themselves, either colliding or moving around, which we'll talk about. Radiation is heat transfer without any matter. So it's it's separate enough that we'll treat it as a different topic. Conduction is our first one. And conduction is simply the transfer of thermal energy through collisions. One molecule with more energy collides with one with less energy and gives it some of its kinetic energy. Remember that we're talking about different forms of internal energy, and so through a collision, a molecule can give a neighboring molecule some of that energy, as we saw just with our basic classical mechanics. Collisions, we get energy moving between 2 different bodies from that collision. This diagram here is just intended to show if you've got a hot object, the red molecules or particles, and the cold object next to it, the blue ones, then the red object with its higher kinetic energy will bounce into some of the blue ones. Those neighboring molecules will hit each other first, or particles will hit each other first, and so they become a sort of in-between temperature. That's represented by the grey in this diagram. But we've still got these red particles that are hotter on the, in this case, the right-hand object. And now they're next to particles which are a little bit cooler, the grey ones that have lost some of their energy. So those red ones will give some of their energy to their neighbouring grey ones, which would make them slightly hotter than their neighbours, so they'll pass it on, and those ones are slightly hotter than the next row of atoms or molecules in the solid, and they would pass that on. So in that way, through those collisions, they're just always passing energy to their neighbours, and it just travels along right through one object into the other. So that's all we mean by conduction. Hopefully that's fairly self-explanatory, right? A collision of particles, not self-explanatory, but fairly simple to understand. Collisions of particles, and they transfer energy through that. When we have to think about the actual heat flow from conduction, when we're talking about how much energy is actually being transferred through this method, then we need to think about some of the properties of the system we're looking at. So we've got an example system on the right here of our slide. We've got a hot object at the top at temperature T1 and a cold object at the bottom at temperature T2. We don't know the actual temperatures. All we know is that T1 is hotter than T2. They could both be really freezing cold, as long as there's a temperature difference, T1 being greater than T2. That's what we're talking about for the setup. As you can hopefully imagine, these things, these properties about the system that would affect how the heat flows. Because the heat is requiring one molecule to collide with its neighbor, If you have a smaller or larger area, that circle A, cross-sectional area A of our little transfer connector, if that area is smaller, then there's fewer molecules in that area that can do that collision, or atoms or particles that can do that collision with its neighbor. And if you've got fewer molecules that can do the collision, I'm just going to keep saying molecules, for some reason that's the word that's in my head today. When I say molecule, I mean atom, particle, or molecule, any of them. So when you've got fewer molecules that can collide with their neighbors, then obviously you can't get as big a rate of energy transfer. If you've got a million atoms or molecules all on top of the next layer of a million molecules, then each of those molecules can collide with the neighbor, and you get a million of them passing some energy along. If you've got a really tiny one and it's only got 100 molecules in its cross-sectional area, and they can only collide with their 100 neighbors, then that's going to give you a much smaller amount of energy going past with each collision. So as you can hopefully appreciate, the bigger that cross-sectional area, the bigger the heat flow is going to be. You're going to get more heat transferred through this connector. Likewise, we've got L, well, likewise, but opposite almost. If you've got L, then for that heat energy to get from T1 to T2, from our object at the top to the object at the bottom, it's got to go through that many molecules all the way down that connector, all the way down. It's got to transfer from one to the next, all the way down this length L. And that means that the longer L is, right, the longer L is, the more collisions are involved and the slower that heat flow is going to be, right? It's just going to take longer for those collisions to end up passing that energy all the way down this transfer connector. So that makes perfect sense, hopefully. The bigger the area, the quicker the heat will flow, so the bigger Q will be. The longer L is, the slower it is, and so the less Q will be. So that's about the shape and size of this. The other thing that matters is the difference between the two temperatures. If we have T1 being way bigger than T2, right, then that means that the temperature gradient, the difference in temperature from the top of this connector to the bottom, is really big. And that means that these molecules at the top have way more energy than the molecules at the bottom, and that's actually going to help push all that energy along. The really, really energetic ones at the top compared to the ones at the bottom will just pass all the energy along a lot quicker. So the bigger that temperature gradient, the more that heat is going to flow, the quicker that heat will flow. And finally, the material that we actually make this connector out of will determine how much heat can flow as well. And that's just a property of all the different types of materials. They all have their own thermal conductivity. We use the symbol, the letter K as the symbol for thermal conductivity. And that's just something you have to look up once you know what material your connector is made of. So all of those things can affect it. And we write that as an equation, the rate of heat flow. So the change in Q over change in T. So how much heat changes from T1 to T2, or from object 1 to object 2 in some amount of time, is given by K, the thermal conductivity, times the cross-sectional area, times that temperature difference, divided by L. So that's all those relationships we've just talked about, how all those things can affect it, but put into a single equation. So hopefully that should all make sense. Also, you should check the units. I'm going to tell you the units for K must be watts per meter per Kelvin, but you should check that that makes sense in the equation we've been given. You can also hopefully see that it might come out to joules per second per meter per Kelvin. So it could be energy per second per meter per Kelvin, or watts per meter per Kelvin. Both are valid and both will show up. There are other units for heat flow that you'll see that pop up. Sorry, not for heat flow. Heat flow obviously is just joules per second. Energy per time, heat joules per second, so it's going to be in watts. But when you're talking about K, you'll see other units, not just watts per meter per Kelvin. You'll see various different units pop up, and you should hopefully be able to recognize them. Sometimes if the connector, which I've drawn as a nice uniform cylinder from the top object to the bottom one, sometimes that's not constant. So the area might change, the material that it's made of might change, which would change K as it goes through, in which case you can't necessarily determine Q for the whole object easily. But what you can do in such cases is do the instantaneous heat flow across some infinitesimal cross-section of the conductor. So you might take, for example, that little circle that I've drawn exactly in the middle. Well, it's not exactly, but I've drawn a circle in the middle. You might take that as an infinitesimally thin slice of that connector. And at that one tiny little slice, the rate of heat flow, so it's still joules per second, energy per second, it now becomes minus Ka times the temperature gradient at that point. For the overall heat flow, we talked about the difference in temperature over the length, and that's just, this is the same concept, the change in temperature per unit along the length of the conductor is our, you can think of it as like the slope of the temperature. If the temperature is some value here and it goes up to some value here, then you're going to have, if you graphed it, you'd have a graph of temperature changing from lower to higher as you went up. And you can think of this as the slope of the graph at that point. When it's a solid, consistent material like we've drawn here, that temperature gradient would be the same everywhere. The slope would be the same everywhere. It just gradually, linearly increases from the low temperature to a high temperature. But if it was made of different materials and different areas or different things were happening, then it wouldn't be a linear increase. But if you did graph the change in the temperature across that whole length, then this would just be the slope of the graph at that point. Hopefully that makes a bit of sense. We won't often go into problems like this. We'll normally deal with ones that are a bit simpler and can stick with our easier equation, but you do need to be able to understand and interpret this equation as well. As I've already said, units for heat flow are going to be watts, joules per second. It's literally defined as rate of heat flow. Heat is in joules, rate is per second. Other considerations. Suppose we calculate the heat flow of the system initially. What happens after that's been going on for a little bit? Well, energy is clearly moving from the hotter object to the colder object, but what result that has in our system is going to depend on the properties of the system. For example, if you've got two really large objects, one hot, one cold, but they're both really, really huge compared to our little connector, then that means that any amount of heat flowing is going to be negligible compared to the actual temperatures of the object. The internal energies of the object aren't really going to change. So that means that the temperature of our hot and our cold end won't actually change, and we'll get a constant flow. We'll get a constant heat flow because those two temperatures are never actually changing. When we talk about really big objects like this, things where the heat flow is not having an effect on the temperature, we generally refer to them as thermal reservoirs. That's just our way of indicating that the heat flow that's happening is negligible compared to the internal energy of the object. So even if this runs for a little while as we watch it, the energy of the hot one has not gone down enough to noticeably change the temperature. And likewise, the energy of the cold one has not increased enough to noticeably change the temperature. But if we watch this little connector, we will see heat flowing through it. Of course, on the other hand, if they aren't really big objects, if they're small objects, then that means that we would expect the hot one will get colder and the cold one will get hotter. What this does is change that difference in temperatures. And since the rate of heat flow was proportional to the difference in temperatures, if that difference decreases, then we're going to get a decrease in the rate of heat flow. So that means that the heat flow isn't constant, it'll actually decrease as these two temperatures get closer and closer. As the temperatures become really close, so that temperature difference goes towards zero, then the rate of heat flow is also going to go towards zero. Right, so you'll get this curved rate of heat flow over time. The rate of heat flow depends on the material the connecting object is made from. We talked about that earlier on. Depending on what the atom is, or molecule, or whatever that's making up this object, that will determine how efficient it is at passing that energy along. And we defined K, our thermal conductivity, as being the value that we assign to the object to determine how quickly that heat flows based on the material. And so we should hopefully already know, without shouldn't be any surprise, that high K value will mean high rate of heat flow. We call those thermal conductors, or we sometimes just say conductor. And for a low K value, so one that is not very good at passing that energy along, we'll call it a thermal insulator, or again, just an insulator. If something's a good thermal conductor, it passes the energy along quickly, we get a high rate of heat flow, that means it's a poor insulator. So a good conductor is going to be a bad insulator, and likewise a good insulator is going to be a bad conductor. You can't have something that's good at both. They are just two words for the opposite of something, or opposite of each other. Now, just another note on the terms conductor and insulator. As you'll probably be aware, we use these words for a lot of different things. We can talk about electrical conductors and insulators. Here we're talking about thermal conductors and insulators. But often when we're dealing with a problem, we'll just say conductor or insulator. We won't specify thermal or electrical. And that means that you have to be able to read a problem, figure out a scenario, and understand if someone's talking about a conductor or an insulator, whether they mean thermal or electrical. For this course, we're just looking at thermal stuff. We haven't discussed electrical conductivity or insulation, but beyond this course, with life in general and with science in general, you should always be able to interpret a situation and understand whether you're talking about thermal conduction or electrical conduction or possibly some other kind of conduction. Metals in general are good conductors, and so they are poor insulators, whereas things like woods, fabrics, and air are poor conductors and therefore good insulators. As a little note, it's the free electrons inside metals that actually help conduct thermal energy very quickly through metals, because the electrons are free to move around between the atoms that make up the metal. That means that they can take some of that kinetic energy and move it quite quickly from one atom to another atom. So the electrons help that process. It's one of the reasons that they're good thermal conductors, and of course those free electrons are also the reason they're good electrical conductors. This table of thermal conductivities here just gives us some examples. You'll notice on the left column we've got kilocalories per second per meter per degree Celsius. On the right is joules per second per meter per Celsius. Obviously the joules per second per meter per Celsius, or per Kelvin, remember, same for that, for an interval, it's per Kelvin per Celsius. The joules one is going to be our SI unit, not calories. So this second column is the one that we'll generally want to refer to when we're doing our calculations, because we want to stick with SI units. So you can see that we've got silver, copper, aluminium, and steel are all higher. Steel is actually on the lower end. Steel is not as good a conductor as some of these elemental solids. Steel obviously being an alloy of different materials, iron and cadmium, and then a bunch of other stuff. So we've got the alloy, the way it forms means that it's not quite as good at passing that thermal energy along. But still better than some of these other solids. So we see that ice is 2, and then everything else is less than 1, right down to some of these really good insulators: fiberglass, cork, wool, goose down, polyurethane, and air is actually a really good insulator. Now, we should point out that air is only a good insulator when it's relatively stationary, when the particles in the air are relatively stationary. We've already talked about the idea that air molecules are flying around a room really fast. And that means that we're actually going to get into convection, which is something we'll talk about in a moment. But when we're talking about stationary air, obviously the particles, the molecules of air are still going to be flying around a little bit. But if you can get a chunk of air and keep it in a certain location, then that will act as a good insulator, because it can't move around the whole room. Right? It can only move in a small space. So a lot of fabrics do well because they trap some air in them. When you've got windows, you may have heard of double glazed windows, which have a little pocket of air in between the two glass panels, panes, there we go. And so you can see glass is 0.84, air is 0.023, but so by having a little pocket of air between two glass sheets, you're actually going to have a much lower thermal conductivity overall, and it will help insulate that house. So air is actually really useful. You just have to figure out ways to trap it in place so that we're relying on the conductivity of air rather than the convection of air, as we'll talk about soon. When we talk about feeling temperature, we talk about how hot or cold something feels. We're actually talking about heat flow. We don't feel the exact temperature of an object. What we feel is how quickly our hand, or whatever part of our body is touching it, is gaining or losing thermal energy. If we gain too much, then we feel hot. If we gain even more than that, we'll start to burn. If we lose too much, we feel cold. And if we lose even more than that, then we'll actually start to get frozen, we'll get frostbite or other damage to our cells from the loss of energy. Since it depends on how quickly we lose that heat flow, so obviously if you overall just lose too much, then you will lose too much body temperature, and that's not good either. But when we're talking about something feeling hot or cold to the touch, we're talking about the speed of that heat flow. So that means it's the conductivity of the material that we're actually feeling. We're telling, that's what's telling us whether this thing is hot or cold. So you can have two objects at the exact same temperature, and if you touch one that's got good conductivity, so in my diagram here we've got marble, which has between 2 and 3 watts per meter per Kelvin, that will feel colder because we get a higher rate of flow than cork, which only has 0.04 watts per meter per Kelvin. Right? So that will feel warmer. So these two objects could actually be at the exact same temperature, but because, so say room temperature, say they're at 20 degrees Celsius, but human body temperature is higher than that. So that means there's a temperature gradient between your hand and the object. The temperature gradient results in heat flow from your hand to the object, but of course the higher conductivity one, the one with the the higher thermal conductivity constant K, is going to take more heat more quickly, have a higher rate of heat flow, and so therefore it will feel colder because you're losing more energy to it. So that's what we're talking about when we talk about feeling temperature. Obviously, it does require that those objects are at a different temperature from you, from your skin. If your hand was the exact same temperature as the surface of the object, then you wouldn't feel hot or cold. It would just, you'd get no heat transfer at all. It would feel exactly the same as you. So it does require a temperature gradient, but then the rate of heat flow depends on the conductivity, and that's what helps us determine whether something's really hot or cold. We talk about K for a material being independent of the size of the object. So just like density, if you've got some material, it doesn't matter how much of it you've got, the K for that thing is always going to be the same if it's just that material. So that is, it's an intensive property. Remember the definitions of intensive versus extensive. So that is intensive, but sometimes it can be useful to have a value for an object which takes into account the size of the object. So you might have a specific insulation covering for some object, and you want to know about that rather than having to calculate based on the thickness of it. You want to be able to calculate, you want to be able to know the thermal conductivity of it for the object overall as a whole. And for that purpose, we use thermal resistance, and it's just based on the length, the thickness of the object, so how far that heat would have to flow, and the thermal conductivity of that material K. So we have thermal resistance R being the length or thickness of the material over K. So a thicker object will have a higher thermal resistance than a thinner object made of the same material. Thermal resistance, therefore, is an extensive property. It depends on the actual dimensions of the specific object that you are looking at. So it's, if we use an analogy with density, density is intensive, mass is extensive. You make a bigger object, you get more mass, even though the density hasn't changed. Here we've got the thermal conductivity is intensive, doesn't matter how big the object is, but if you make a bigger object, you're going to get a higher thermal resistance, so it's extensive. As an example, let's look at a window pane. So we've got a 1.5 meter square window made of 2.5 millimeter thick glass in a house which is being heated by a fireplace on a cold day. So that means the inside is going to be warmer than the outside, and we will therefore have a temperature gradient, and we will therefore have some temperature flow, some heat flow through this glass pane. The temperature of the air on the inside surface of the glass is 14 degrees Celsius, and on the outside it's 6 degrees Celsius. What is the rate of heat loss through the window? We've been given the K for glass. So I could do this one on the document camera, but it's actually a pretty straightforward calculation, so I'm not going to bother drawing anything. There's not a lot I can add to this. We will point out, though, it is important to note that in this case, we're treating the inside and the outside as thermal reservoirs. We're going to say that even though we're losing some energy through the window, the fact that we're constantly heating the inside means that that's going to stay at pretty much the same temperature, even though it's losing some energy. And obviously the outside is not going to be noticeably warmed up by the fact we've got a fireplace inside. That's not going to heat up the entire Earth's atmosphere. So we're going to treat these two sides of our window as thermal reservoirs, and that means that our heat flow is going to be constant. It's not going to change as the heat flows. So what's the rate of heat loss? we just use our formula, K times A times the difference in temperatures divided by L. You've been given everything here. We have to calculate the area based on the 1.5 meters square. So that's 1.5 meters square window. You may interpret that as being a 1.5 square meter window, which is different from a 1.5 meter square window. So the area here should be 2.25, just to be clear about that. Normally exam questions would be less ambiguous than this example. The thickness or length that the energy has to go is 2.5 millimeters. And of course we want SI units, so convert that to 2.5 times 10 to the negative 3 meters. And we've been given the temperature difference, 14 down to 6. So we've got a temperature difference of 8 degrees C or 8 Kelvin. And then we just plug all of that into our equation, and there's our result. We've got area, length, K, difference in temperatures, and we get 6,000 watts. So the rate of heat flow through this entire window is 6,000 joules per second. So obviously constantly losing energy, but as we said, not enough to treat the two sides of this window pane as not being reservoirs. We can still treat them as reservoirs. So that's conduction. We're now going to talk about convection. If you imagine a little bit of fluid sitting in a beaker or a pot, and you're heating the bottom of this pot of fluid, then that means the molecules at the bottom, the fluid molecules at the bottom, will get more energy. Remember that when things get more thermal energy, they're moving around more, they've got more kinetic energy, and that means that they're basically going to be pushing the other molecules further away from them because they want more space to move around in. And if they're pushing the other molecules away from them, that means that that bit of the liquid is actually now less dense. There's more space between molecules, and that's how we define density, is how much mass there is per unit area. If we've increased per unit volume, if we increase the volume each molecule needs, then we've increased the space overall per molecule, which is decreasing the density. But as we also talked about, when you've got something with less density, it's going to float. Right? It's going to float in a fluid of higher density. So now you can think of the hotter bit of fluid as one object with a lower density than the colder bit of fluid as the second object. And that means that the hot bit will float within the cold bit, and so the hot molecules will rise up through that cold liquid. That's just due to the buoyancy force, exactly what we talked about when we talked about pressure and density and buoyancy and all of that. But now we're thinking about it in terms of each sort of molecule and the space around it, how much space it needs because of how quickly it's moving. So it can be a little confusing, but hopefully you can grasp the general concept. It's that lower density that causes that little pocket of hotter fluid to then rise up inside the colder fluid. And that is natural convection. Right? Convection caused by this change in density due to the heating of the fluid. So convection is resulting in heat transfer because the heat was at the bottom of the fluid, then it rises up. Now the heat is at the top of the fluid. Right? So we've had motion of energy through the fluid, even though the energy won't necessarily have changed from one molecule to another. That does happen, of course, because these molecules will collide with each other. So we do get some conduction as molecules collide with each other. But overall, most of the energy has stayed with that particle as it's gone from the bottom to the top of the fluid. So the energy of the fluid overall has moved from the bottom to the top. And obviously then if you're constantly applying heat, the new molecules now at the bottom are going to get heated and they'll do the same thing and they'll go up. And so you get this constant flow of molecules going to the bottom cold, heating up, and going to the top hot, and then they'll bounce into others, slowly cool down, and then end up back at the bottom and get heated again. And overall the fluid will sort of just constantly mix this way. So convection is the way that energy is moving throughout the fluid, as opposed to conduction, where the molecules stay where they are and bounce into each other and pass the energy along. Here, the molecules keep their energy, but they move themselves overall from one place to another. Forced convection is the same idea, but we force it, right? We have a fan or we stir it so that the molecules with the hot energy will get spread throughout the entire fluid. So forced convection is just, we want the thermal energy spread throughout the substance, the fluid, so we force it to get spread throughout the fluid by pushing it. We either do that with a fan, or you could stir something with a paddle wheel or whatever, or a spoon if you're cooking. So we force it when we're stirring it. Couple of examples. All weather. All weather is strongly influenced by convection. Warmer air rises, colder air gets pulled in underneath, that's creating wind. Similarly, in the ocean, if you've got some warmer or colder waters next to each other, they're going to move relative to each other and we get ocean currents. So a lot of weather phenomenon all depend on convection, just the idea that the temperature of a fluid changes its density and therefore will move relative to some other part of the fluid that's got a different density. And closer to home, well, not closer to home, weather's everywhere, that's perfectly close to home, but inside your home, when you're cooking, you have water in a pot. The water at the bottom will heat up, rise up, and then the cold water will go down the bottom, that'll heat up, rise up, and so on and so on, and so you're actually just stirring itself. That's why we don't need to stir water in order to heat it up. Water will stir itself. But if you get some thicker foods, some thicker fluids or substances, you may need to actually stir them because the changes in density and the viscosity, which is how thick or gloopy that stuff is, how sticky it is, that may prevent it from effectively stirring itself. So we do have to stir thicker foods, but thinner foods like water or some teas and coffees and things like that, we don't necessarily need to stir. Coffee is probably a bad example because you normally stir it to make sure the coffee dissolves. But anyway, things like tea, you don't generally need to stir because the water will stir itself through convection. Convection, though, is very difficult to model. Right? How are we going to model the flow of all of these different molecules as they gain heat, and where are they getting the heat from, and how much heat do they have relative to the other ones, and understanding all of that is very difficult. That's part of the problem in trying to model weather systems. You've got to understand all this convection flow. We do have models for it. They're advanced, they're difficult to understand and to create. So we won't be going down that path in this course. We just want you to understand qualitatively. So remember the difference between quantitative and qualitative. Qualitative is the ideas, the concepts, the sort of the quality of a thing. Right? It's how you would describe it and think about it. Quantitative is where we have numbers, where we bring in equations. So for conduction, we talked about it qualitatively, then we brought in some equations and did some quantitative discussion and had some equations. That's where the math comes in. For convection, we're just going to stick with the qualitative part. We want you to understand and explain and describe and be able to look at a system and say, hey, in that position, this should heat up and then we'll get some convection this way and that should happen. And do that kind of approach, but we won't do any of the equations or calculations. So that's the content for this topic 2. As usual, there's a review there. Take your time to check through that, make sure you're happy with everything, and I'll do another video shortly that will cover off some problems using conduction and convection.